this conference. The organizers actually constrained me to discuss the evolution of the experimental searches for neutrinoless double beta decay and 2-neutrino double beta decay. And this is not my kind of horse of battle. So I struggled. Now the result of this struggle that I became to appreciate, became to appreciate the tenacity, the strength, and the imaginative power of our experimental colleagues who do these experiments. For me, I mean, it looks like that you have people, also their patients, who sit deep underground and they wait something to happen, and it happens once. I mean, you have one event in a few months or even in a year, and you are happy with that. So, I mean, this is not for me. Okay, so let me try to follow this path. I don't know how successful I'm going to be, but let me begin with few statements which are relevant to the topic. Now, I think that all of you will agree that determining the status of lepton charge conservation and the nature, Dirac or Majorana, of massive neutrinos is one of the most challenging and pressing problems in present-day elementary particle physics. Now, the question about the nature of massive neutrinos is a question about fundamental symmetries of particle interactions. Dirac neutrinos are possible if there exists some form of conserved lepton charge. In particular, this could be the total lepton charge, and neutrinos are different from antineutrinos by the value of the charge they carry. Now, Majorana massive neutrinos are possible if no lepton charge is conserved, and as you know, seesaw model of neutrino malgeneration predicts massive Majorana neutrinos. Now, there is a problem with the assumptions of conserved lepton charge because it is related to the existence of global Yuan symmetries, and according to very wise people, in modern understanding of particle physics, global symmetries are approximate. I mean, I'm quoting from a paper by Witten, and the same view was expressed by Weinberg in the interview he gave from CERN Courier. So if we follow this path of thought, we can expect that at certain level, neutrinos should have a Majorana mass, and therefore neutrinoless double beta decay should exist. Now let me add also that establishing that the total lepton charge is not conserved in particle interactions by observing neutrinoless double beta decay would be a fundamental discovery similar to the establishing baryon number non-conservation by observing, for example, proton decay. And establishing that massive neutrinos are Majorana particles would be of fundamental importance, as important as the discovery of neutrino oscillations would have far-reaching implications, of course. Now, to the subject. Of course, at the beginning there was Pauli, which was discussed. Then there was Fermi, which was discussed. And then comes Lisa Meitner in 1935, who was the first... Sorry, you're right. Maria Goeppert-Mayer, who was the first to discuss 2-neutrino double beta decay. This is a copy of the first page of the article he published. And she follows the Fermi theory, and she realizes that for some even nuclei for which single beta decay is forbidden, actually this process would be allowed. And she noticed that this will be a second order in the beta decay Hamiltonian. And she writes that the process, the simultaneous occurrence of two beta decay transitions, each of which does not fulfill the law of conservation energy separately. She goes on to calculate the rate, and she finds, I mean, in the abstract, she gives a lower bound of 10 to the 17 years. However, she gives some examples, and she arrives at rates of the order of 10 to the 20 years. And this is not far from what is actually the rate that is measured in contemporary experiments. Now then, Majorana, I will skip that because this was discussed. And then comes Racah, 1937. Now, actually, if you read carefully the paper of Raka, you realize that he did not discuss neutrinoless double beta decay, but rather pointed out how it might be possible to distinguish between Majorana and Dirac neutrinos in the process of inverse beta decay using free neutrino beams, and this is the also view shared by Pontecorvo. He notices that if neutrinos are Majorana particles, that is they are identical with their antiparticle, and neutrino is produced together with electron in beta decay, then when interacting with a nucleus, it will, the inverse beta decay process, it would create an electron rather than positron. If it were a Dirac particle, it would have created a positron. And he points out that this is a possible method to actually distinguish between Dirac and Majorana neutrinos. Then Furry is the first who really discusses neutrinoless double beta decay. And he assumes that neutrinos is Majorana. He uses the Fermi theory of beta decay. And he points out that according to this theory, if neutrinos are Majorana particles, two neutrons, by exchanging a virtual Majorana neutrino, can transform into two protons with two electrons in the final state. He goes on to do calculation of the rate, and he does it in 4 fermion interaction, several scalar, pseudo-scalar, vector, vector, assuming that neutrino mass is 0. And he finds that the rate, the main conclusion, due to the phase space factor, can be by a factor of 10 to the 5 faster than the rate of 2 neutrino double beta decay. And he compares his results with the calculation of Goeppert-Meyer. Now, 1940 to 1960. The main motivation for the experiments searching for neutrinoless double beta decay in that period is the same as it is today. The question of the nature of massive neutrinos. Now, theory was predicting values of neutrinos double beta decay half-life of the order of 10 to the 15 years, while for the 2 neutrino decay, it was in the range of 10 to the 20, 10 to the 21 year. The first experiment searching for neutrinoless double beta decay was done in 1948 by Fireman, and this was done with tin, 25 grams, enriched to 54% using Geiger counters, and he gets this limit on the half-life. Positive results were claimed by a number of experiments in that period, and they were disproved by later data. Then the first search for double positron neutrinoless decay was performed, and also the first search for E minus E plus conversion on nuclei. Now, I should say that my impression is that even at that time, the most advanced experimental methods and detectors were used. Nuclear emulsion, Geiger, proportional, and scintillator counters, Wilson chambers. People realized that they have to use enriched isotopes. People also realized that in order to shield background, one has to go underground. As deep as possible. And the sensitivity reached in that period was 10 to the 7, 10 to the 18 years for neutrinoless double beta decay. The first neutrinoless double beta decay experiment in USSR was done in 56 with calcium-48. Now, in 49, also the first geochemical experiment was performed searching for this transition of tellurium-130 to xenon-130. Sorry. This technique consists of separation of xenon from ancient up to several billion years old minerals and subsequent isotope analysis. And then the detection of excess amount of xenon-130 after, of course, one takes into account obvious, mundane contributions, would imply that the decay either into two neutrino double beta decay or neutrinoless double beta decay took place. The authors got this limit. In 1950, Ingram and Reynolds did the same experiment using the same method, and they observed, actually, they deduced a positive value. I mean, they quote a value for the half-life of 1.4 10 to the 21 years. This, much later, was confirmed experimentally. Actually, the current value measured by Quarry Zero experiment for the 2 neutrino double beta decay is this one, and the value quoted in 1950 is within the 3 sigma allowed region of measured value. Now, there are, of course, related developments which played very important role in this period, 1940-1960. The neutrino was observed, the parity non-conservation. First it was hypothesized, and then it was proven to take place in beta decay. The 2 neutrino component theory was proposed. The helicity of neutrino was measured in the experiment of Goldhaber, Sunyar, and Grodzin, and it was turned out to be -1. And most importantly, the universal V-A current theory of weak interaction was proposed by Feynman, Gell-Mann, and Sudarshan and Marshak. This had very important implications for the, before going that, let me also make the comment that in 1958, Pontecorvo put forward the idea that the neutrino which is produced in weak interaction processes is actually a linear combination of the states of 2 Majorana neutrinos, which have definite but different masses, with maximal mixing and opposite CP parities of Majorana particles. This was the first time that the hypothesis of existence of fermion mixing in weak interaction Hamiltonian was put forward. In the paper of Makina, Kagawa, and Sakata, which considered a specific model based on hadron-lepton symmetry, the nu E and nu mu are linear combinations of 2 Dirac mass eigenstate neutrinos, and the mixing angle, because of this hadron-lepton symmetry, is actually equal to the Cabibbo angle. Now, the next period, from 1960 to 1980, the fact that the weak interaction has V-A structure soon was realized to have very strong implications for the predictions of the rate of neutrinoless double beta decay. Actually, the first to realize that was Grueling and Witten in 1960, which calculated the neutrinoless double beta decay rate in the case of V-A theory plus nu E being a Majorana particle with non-zero mass, or with 0 mass, but in the presence of also right-handed currents. They were the first to realize and to point out that the issue about the existence of neutrinoless double beta decay is actually related to the issue about the conservation of the total lepton charge. So it was a very modern approach to the problem. They also found out, by doing the calculation, that the decay rate in the case of absence of right-handed currents is proportional to the square of the mass of the Majorana neutrino, while in the presence of right-handed currents and 0 neutrino mass is proportional to the admixture of this right-handed neutrino current squared. Okay. Now, on the experimental side, the first counter experiment in which the detector was equal to the source was performed with calcium-48 by this group, I mean two authors actually, and this limit was obtained. In 1967, Fiorino et al. Used for the first time germanium-lithium detectors, germanium-lithium detectors, with the first limit that they obtained was this, but the final limit was roughly by a factor of 10 beta, 5 times 10 to the 21. Wu performed a series of experiments in which she was using tracking the technique, that is, visualization of tracks and measurement of the energy of the 2 electrons in the final state. And the experiments were done with calcium-48 and selenium-82, and these are the lifetimes that have been obtained. In this period, several geochemical experiments were performed with tellurium-130, selenium-82, and tellurium-128. And Till Kirsten participated in one of them, in which I think results for tellurium-130 were obtained. No, with selenium, I think. Yeah, sorry, with tellurium-128. Till. Selenium-82. Okay. Actually, this is what is written here. Thank you. So they observed the two neutrino decay rate. Actually, they observed two electrons in the final state without knowing whether this is two neutrino or neutrino-less double beta decay. Now, the related developments in this period, according to me, are the following, which are relevant also for this discussion. In '67, Pontecorvo introduced right-handed neutrinos as sterile or inert and considered, in addition to nu-e, nu-mu active neutrino oscillations between active and sterile neutrinos. And in that paper, he also predicted the existence of the solar neutrino deficit. In '69, Gribov and Pontecorvo considered for the first time a mass term, which actually generates, when you diagonalize it, generates massive Majorana states. And in '76, Bilinki and Pontecorvo generalized this to the case when also right-handed neutrinos are present. They consider this what we call today Dirac plus Majorana mass term, and which is widely used in the seesaw mechanism of neutrino mass generation. I think they were the first to do that. Now, in '77, Halprin et al. Realized that actually you can use the lower limits. On neutrino-less double beta decay half-life in order to obtain lower limits on the mass of the heavy Majorana neutrino. And from the existing data, they found out that this limit, the most conservative case was about 3 GeV. This is the current version of the same argument, where one shows the limit in the plane of the coupling squared of the heavy Majorana neutrino to the electron in the weak lepton charge current versus the mass of the heavy Majorana neutrino. And you see that at 3 GeV, this is about 10 to the minus 8 on the coupling squared. Now, 1980 to 1990s. There was a revival of interest, of course, in neutrino-less double beta decay. And one of the reasons was, of course, the development of gauge theories of electroweak interactions and more general gauge theories, where it was realized that actually in these theories, they can naturally incorporate L non-conservation and massive Majorana neutrinos. Then the seesaw mechanism leading naturally to massive Majorana neutrinos was proposed. Leptogenesis scenario of generation of baryon asymmetry was also proposed in that period. Massive neutrinos at that time with mass about 14 electron volts were widely considered as possible dark matter candidates. And in 1980, Lyubimov claimed the observation of neutrino mass of 20 electron volts, which later, of course, were shown to be an incorrect result, but still it played a role in stimulating further research. Now, on the theoretical side, in 1980, 3 papers appeared, May, June, and July. And in all these 3 papers, it was realized the presence of Majorana phases in neutrino mixing matrix in the case of massive Majorana neutrinos. Actually, if you have n families, these 3 groups realized that the PMNS matrix will contain n-1 times n-2 divided by 2 Dirac phases, and n-1 additional Majorana CP violating phases. And in this case, even in the case of n equal 2, that is the mixing of only 2 Majorana particles, you can have 1 CP violating phase in the mixing matrix, which of Majorana nature. In the paper, which appeared in May, it was also realized that flavor neutrino oscillations are not sensitive to the Majorana CP violating phases, and thus they are not sensitive to the nature of massive neutrinos. This result was shown to be valid also in the case of oscillations in matter later. The general conclusion was that you cannot try to determine the nature of massive neutrinos in neutrino oscillation experiments because they were not sensitive to it. In the paper which appeared in July, for the first time, the effective Majorana mass was written in a way that showed very strong dependence on the Majorana phases. And these authors concluded that depending on the values of these phases, you can have actually cancellation between these three terms. And therefore, I mean, Majorana phases play a very important role in the phenomenology of neutrinoless double beta decay. Now, in 81, Lincoln considered the case of CP invariance and pointed out that Majorana neutrinos can have definite CP parities, in this case equal to plus minus I. And the phases, the CP invariant values of the phases are 0 plus minus pi. And the phase factors which appear in the effective Majorana mass take values, in this case, plus minus 1. And these are the relative CP parities of the corresponding pairs of massive Majorana neutrinos. Now, in 1980, I attended a school in Erice where Wigner was present, T.D. Lee was present, Steinberger, Sakurai, and others. And I will skip this for the discussion session. I mean, the Wigner's question. In 81, for the first time, neutrinoless double beta decay with emission of a Majoron was considered in the paper by Georgi, Gleshov, and Nusinov. Now, in 82 came the famous black box theorem by Schechter and Vallée, which stated that the observation of neutrinoless double beta decay imply, in gauge theories in particular, the existence of Majorana mass term for the electron neutrino. So this independently of the mechanism which generated the decay. Now, this is an example of how this can happen. It's very simple to realize how this does. If you write an effective dimension 9 operator which generates neutrinoless double beta decay, and then you add to it the beta decay Lagrangian. Now, it's a for loop effect. However, the quantitative nature of this statement was analyzed by Dürr et al. In 2011, and they concluded the following. Although the principal statement of the Schechter-Vallée theorem remains valid, we conclude that the black box diagram itself generates radiatively only mass terms which are many orders of magnitude too small to explain neutrino masses. Therefore, other operators must give the leading contribution to neutrino masses, which could be of Dirac or Majorana nature. This is an example of, I mean, this is the general structure of the effective Lagrangian they have used in this analysis. And this is an example of the value that one gets through this for loop diagram by the term which is called here epsilon 3. I mean, it's 10 to the minus 28 electron volts. You forget about it. Now, nuclear matrix element calculation come into light in focus of discussion starting from 84 with the paper of Huxton and Stevenson, which noted in particular that the nuclear matrix element for neutrinoless double beta decay and two neutrino decay are completely unrelated. Thank you. Then comes a very detailed study of this subject in a paper by Doi et al., which they also worked with right-handed currents. And in this paper, energy and angular distribution of the two electrons calculated in the mass mechanism and the right-handed current mechanism was done. And it was pointed out to the possibility of distinguishing experimentally between the two mechanisms using the difference between the respective distributions. In 86 comes the paper of Peter Vogel and Zirnbauer, who demonstrated that the inclusion of the particle-particle interaction in the models within the quasi-particle random phase approximation method permits to calculate the rate of two neutrino double beta decay with relatively small uncertainties. This result led to extensive use of this method for the calculation of two neutrino and neutrinoless double beta decay matrix elements. Now, experimental activity. Relatively large and relatively cheap germanium detectors appeared at that time, and they were used to push the limit on the lifetime for germanium-76 to the range of 10 to the 23, 10 to the 25 years. I mean, one of the first experiments to do that was that by Caldwell in 1991, where he used, 7.2 kilogram of high purity natural germanium semiconductor detectors and obtained this limit of 1.2 10 to the 24. Experimentalists were going further down and down underground. Then a similar technique with, however, germanium enriched to 85% was used for the first time in the ITEP Yerevan experiment, which is the limit they obtain is of the order, similar to that obtained by Caldwell. They also observed 2 neutrino decay with this rate and obtained a limit on the Majorana emission of about 10 to the 20 years. This progress led to the Heidelberg, Moscow, and IJEX experiments with enriched germanium with sensitivity of 10 to the 25 years. Limit of the order of 10 to the 23 was obtained with xenon 136 in an experiment in which the energy of the 2 electrons was measured in vents with simultaneous emission of the 2 electrons from one point were selected and the tracks of the electrons were reconstructed. This is like what was done in the NEMO experiment. And in 1984, Fiorini and Ninikovsky proposed, following the idea of Misselmacher, Neganov, and Trofimov from Dubna, the use of low-temperature bolometer detectors to search for neutrinoless double beta decay. This idea was realized successfully in the Curicino and Cuore experiments. Now, the breakthrough result was in 1987 by Mo et al., who for the first time observed the 2 neutrino decay of selenium-86 and measured the half-life. This is the value. This was followed by a number of experiments in which 2 neutrino decay was observed also. The list is here. I will just move a little bit faster. Geochemical experiments were also performed in the 80s. For example, the first geochemical experiment with zircon 1996 was performed, and this value was obtained by Kawashiva and collaborators. TIR and collaborators also measured the half-life of tellurium-130 with this value. However, a competing experiment by Manuel reported a somewhat smaller half-life. At the time, this discrepancy were not understood, but later it seems that the smaller values were shown to be correct. Now, first decay of the 21st century, no time, very briefly. So, in 98, atmospheric neutrino oscillations were discovered. In 2001, 2002, solar neutrino flavor conversion was proven to take place. And in 98, the Shaw experiment obtained a strong limit on sine squared theta 2 theta 1, 3. These are the Shaw results. I plot them here because on the ratio of the measured spectrum to the predicted spectrum, in the region of 5 MeV, you see the bump, even in the Shaw experiment, actually, indication for the bump, which is widely discussed these days. Now, this led to determination of the parameters del times square atmospheric, del times squared solar, and sine squared theta 1, 2, with relatively good precision, and this limit on sine squared theta 1, 3 from the Shaw experiment. And the development led to the realization that the measurement, the neutrinoless double beta decay via the measurement of the effective Majorana mass can provide information on the type of neutrino mass spectrum, the absolute neutrino mass scale, and with additional input on the absolute neutrino mass scale also on the values of the Majorana phases. This can be easily explained using this diagram, but unfortunately time is short. This is the result of the IJEX experiment, which was performed in Canfranc laboratory in Spain. they used actually Roman lead to shield the detector, which was more than 2,000 years old. And this is the limit they obtain. Then we come to the Heidelberg-Moscow saga, but I will skip it because it was widely discussed. The only thing I will say that it was the result of Clapdor was et al. Was definitely ruled out by the results of the Gerder experiment with this limit of 8 times 10 to the 25 years. Now, Cuoricino and Nemo played very important role in this field in the years starting from 2000 to 2010. In particular, Cuoricino obtained a limit on tellurium-130 neutrinoless double beta decay lifetime of 2.8 10 to the 24 years. And Nemo, with a very large amount of molybdenum, obtained this limit on neutrinoless double beta decay of molybdenum 100, 10 to the 24 years. But what Nemo did really in really remarkable fashion was to measure the two neutrino double beta decay half-lives of a large number of nuclei, calcium-48, selenium 82, zircon 96, molybdenum 9, and so on. For molybdenum 100, they had about 700,000 two neutrino double beta decay events. So this is one of the beautiful events which Nemo 3 obtained. It's a two neutrino double beta decay event, as you can judge from this curve here. Now, latest results. We are today, I quoted Gerda. This is the result from Cuore and Cuoricino, the latest one on tellurium-130, 1.5 10 to the 25 years. And this is the Kamland result with xenon-136, 1.07 10 to the 26 years, which implies this upper limit on the effective Majorana mass. Now, this could be used to obtain an upper limit on the absolute neutrino mass scale or the lightest neutrino mass, and this upper limit comes to be about 0.6 electron volts. This is the list of experiments which are either in preparation or these are proposals which aim actually to cover the range of values of the effective Majorana mass up to the inverse ordering, inverse hierarchy of neutrino masses. So it's very impressive. I really like the design of these experiments. This is Gerda. They're really beautiful, as many experiments in neutrino physics. Theoretical developments. In this period, non-standard mechanisms of neutrinoless double beta decay were widely considered. The corresponding effective operators were classified, and predictions of possible lepton number violation effects at LHC were investigated. It was shown that the existence of sterile neutrino with mass at the EV scale can change drastically the standard mechanism picture of neutrinoless double beta decay, and considerable efforts were made to solve the problem of the calculation of the nuclear matrix element, but the problem is still not solved. This is the nuclear matrix element for the mass mechanism, and you see that we have uncertainty of the order of factor of 2 or 3, depending on the nucleus. We have the GA quenching problem, which is a problem related to the fact that in nuclear matter, the axial coupling constant gets modified and actually gets reduced, renormalized and reduced. And this is very important because the neutrinoless double beta decay half-life is inversely proportional to the fourth power of this constant. Now, let me say that the reduction of GA is necessary in various models. Calculations of two neutrino double is necessary in various model calculations of two neutrino double beta decay to reproduce the data. This does not imply that the same reduction of GA takes place in neutrinoless double beta decay nuclear matrix element, and there are indications that the reduction is much smaller. Actually, the mechanism of quenching is not understood at present, and thus the degree of quenching cannot be firmly determined quantitatively and is subject to debates. And I will conclude with this quote from the authors of 1956 paper on neutrinoless double beta decay. I mean, this is the experiment done in Soviet Union. The search for double beta decay is an amazing example of fantastic succession of periods of hope and disillusionment. 2 times in the course of a single decade, this phenomenon has been discovered, and both times the discovery has been found to be erroneous. The history of the question is still not complete. The phenomenon has not been observed experimentally, and the succession of journal articles in recent years only gradually sets larger and larger lower limits on the lifetime of a nucleus capable of double beta decay. In the present research, we have again not succeeded in observing the event, but the limit on the half-life of the process of, this is neutrinoless double beta decay of calcium-48, has been raised to about 10 to the 9 years, and further steps in this direction will depend on the achievement of achieving considerable increases in the amount of material subject to study. So the question for the nature of massive neutrinos and the status of lepton charge conservation, of course, continues. Yeah, thank you.
There has been a paper by Cyriliano and collaborators saying that in the computation of the nuclear matrix elements for neutrinoless double beta decay, some short-range contributions had been omitted so far, and that taking them into account could change the predictions. Can you comment on that?
Which paper is that?
A paper by Cyriliano et al.
Cyriliano et al. No, I don't think I can comment on any specific paper on this subject. If you know that, I mean, you may.
I'm not aware of this.
Yeah.
There was, I didn't read the paper, but there was in May this year. You know, there is this from physical revulators. Every week they send an email with some articles published in PRL which are shortly commented. So I know it only from
maybe
from
if
this.
Peter Fogel is here, he might have a comment, but I don't see him.
I don't think he's here.
Okay, they were mentioning that this could be there could be a cancellation or an addition, positive interference with the other contribution that had been included so far.
No, I mean, when you have multiple mechanisms which contribute to the amplitude, you can have all sorts of things. I mean, you have can have amplification, you can have cancellations. It depends on the relative phases. So the story is rather complicated.
I think they were speaking in general. I mean, they were thinking of the mass-induced mechanism, not adding additional mechanism. Their comment was more on the computation of the nuclear matrix elements.
Okay.
Anyway, if everybody knows this paper.
Let me say that one should not be afraid of the possibility, if neutrinoless double beta decay observed. I mean, of course, one would like to know what is the mechanism triggering the decay. And there are methods developed, we know how to do it, in order to figure out which of the possible mechanism, even if more than one mechanism is involved, is contributing to the decay. Of course, you need data from more than one nucleus. I mean, you need data from several, as many as possible nuclei. But I guess that if neutrinoless double beta decay will be observed in one nucleus, I mean, it will be observed also in the other nuclei. That's for sure.
I have a comment concerning, Sergei, the quenching problem. Indeed, I'm very surprised that this came into the game, sort of say, very recently, because the quenching problem is known in nuclear physics since many decades. And all the people working in weak interaction physics or gamma-Teller transitions, charge exchange reactions are very well aware of it, and all the debates that have been going on for many, many years, because in nuclear physics people were not really solving this. So when I started hearing this into the context of neutrinoless double beta decay, I was very surprised, because this is very well known.
In neutrino double beta decay, it came through two neutrino double beta decay.
I know, but
Through, and that's why I'm a bit, how should I put it? I mean, really, we don't know what is happening in neutrinoless double beta decay.
Sure, but for example, in neutrino nucleus cross sections, also you can have contributions from forbidden transitions, and we also don't know the quenching, how much of it is eventually there for the forbidden transition. And that was already said many, many years ago. So I'm very surprised, but okay.
Also, I should say, neutrinoless double beta decay experimentally should not be afraid of the quenching so far. So keep cool.
No.
Because we don't know what it is.
Yeah, sure, we don't know. But just the fact that people have started discussing this issue, which is very well known, only recently.
Also, neutrinoless double beta decay is very different from the two neutrino decay in the sense, in the fact that the momentum exchange is much larger than in two neutrino double beta decay. I mean, it's about 100, 200 MeV.
Sure.
And the dynamics can be completely different from the two neutrino decay.
Sure.
Is there, you showed a whole list of experiments planned. Is there a coherent plan to get down to the mass differences that would be implied by the mass hierarchy to be normal?
Now, the only people who somehow dare to talk about that, I think, is the people from the EXO collaboration, which are planning for something called NEXO. And according to their estimates, I mean, this will be a ton detector.
Right. Is that enough?
Huh?
Is that enough?
Ton is pretty much, it's a big amount. Huh? And according to their estimates, they can reach the upper part of the normal hierarchical prediction, like 5 times 10 to the minus 3 electron volts in MF. Now, in effective Majorana mass, of course, everything depends very strongly on this issue of quenching of GA.
But how much would that cost?
I have somewhere a table of the cost, but I cannot tell you. But it's manageable for this type of, for the material that they plan to use. Xenon 136, it seems manageable.
It's just that we spent 5 billion trying to find the Higgs, and I think this is a question of similar importance. So I don't think one should be shy with those experiments.
I think it will cost less at the end.
Well, does it work? So there's estimation by Barabash who. So Alan, you can find a paper by Barabash who precisely addressed this question. So if it is just normal hierarchy, what are elements and what is the mass? At least 10 tons of enriched, so that's not enough. And the cost is more than billion, certainly, for this. It's 10 years observation, a very low background, which is also issue in this case.
No. He's referring to values of M effective of the order of 10 to the minus 3 electron volts. I am talking, but the interval, if you look at the current prediction, is somehow between roughly, no, unless you fall in the in the wall, yes. If you don't fall in this low region, the prediction is between 2 and 5 10 to the minus 3 eV for hierarchical spectrum.
Yeah, this is what precisely Barabash is using. We can look at the paper.
I don't think it's a million. I mean, these guys are talking about something realistic of doing it. And they're talking about sensitivity of the order of 5 times 10 to the minus 3 eV. So it's something manageable. That's for sure. About the time.
You know, Sergei, I guess by quenching you mean GA over GV, right? I mean, that's the one, how it changes. The actual coupling constant.
Sure,
That's
but,
okay.
but
I'm just-
GV
but
doesn't change because
It
it's
doesn't
related
matter.
to
I'm
a
not talking
conserved
about
code.
GV. I'm just saying how, because I remember when I was very, very young, GA used to be 1.18. That was a great puzzle, and it started growing and growing, growing, become 1.25. And actually what came in was current algebra. They came in and you could relate it to cross-sections, pions, and things like that. It was a very complicated Adler-Weisberger equation. I don't know if there are old enough people here who have heard that thing before, and that solved that problem. So do you expect that the calculation, similar thing, I mean, it's going to be harder for heavier, this was for neutron, for heavier nuclei? Is it going to be much, much harder? It's going to be much, much bigger? Or do people know anything about that? I mean, you, of course, are going to have cross-sections of many pions and things like that. I mean,
In the context of neutrino double beta decay, they just don't know. I mean, this is the statement. Of course, people are working on this problem, and I hope that there will be some progress because, I mean, the groups who do these calculations are now really working on this. This is the major problem. So let's see what will happen. I'm not an expert on nuclear matrix element calculation, so I cannot comment more than this. Yes?
Okay.
Waiting the microphone. So thanks, Sergei, what give a good review of experimental results for me as experimentals. But I have a question like experimentalist to theoretician. We know what, at least after the neutrino conference in Heidelberg this year, we also presented what more probably it will be the normal ordering of neutrino mass, and maybe also very no sterile neutrino. So in such a case, it means what in the nearest future, as we already discussed it will be very long and maybe very different and expensive story to go to a normal hierarchy in such a case. If we are speaking only about one mechanism, light neutrino Majorana mass. But I look for the title of your talk here, and here is written double beta decay with or with. So I think it's double decay with, and with, because in my personal collection, it's about 30 different mechanisms, sub-mechanisms, and so on. So my question is now, if we forget, and it will be practically impossible in the next 50 years to reach this light, to observe these light neutrino mechanisms. What is, from the other set of mechanisms, from your point of view, more favorable for us, for experimentators?
First of all, let me point out that what this preference for normal ordering tells you is that delta m square atmospheric is positive. It doesn't tell you that the spectrum is hierarchical, which means that you can be anywhere on this branch up to the limit. You see? So that doesn't mean that you're here. Sorry, that doesn't mean that you're here or here. So we don't know. Concerning this additional new mechanism, some of them have clear signatures at LHC, lepton number violation at LHC. And this will be looked at, and let's see what happened. I mean, we really don't know. And if you ask me whether I have a preferred mechanism, for me the most natural would be heavy Majorana neutrino exchange. It was somewhere, I mean, there is some diagram somewhere. Here. Heavy Majorana neutrino exchange with masses in the range of, say, 100 GeV or TeV. Now, for the time being, we don't have any hint about the presence of these objects at LHC. But, for example, there are proposals for much higher sensitivity to this type of objects in future accelerators like E plus, E minus that Alain is advocating. And even LHC can improve on the sensitivity in the future runs. So let's see what will happen. Of course, these heavy Majorana neutrinos are related to many things. To seesaw mechanism, they're related to the generation of the baryon asymmetry of the universe, and that's why I liked it. Now, whether this is the true mechanism, of course, we don't know.
Okay, let us thank Sergei again.